may not have seen this in algebra 1. I'm going to go ahead and say you probably didn't. We don't know what inverse operations are. Undo an operation, undo addition and subtraction, undo multiplication is division, and so on and so on. When we're talking about inverse functions, it's basically flip-flopping your x's and y values. Now, what happens here is all you're doing is if you have a set of values that don't write these tables out. It's just visual, so you see what happens. What you're doing is you take your values of x and you switch them to the values of y, and then your values of y become the values of x. It's just flip-flopping x's and y's. It's quite literally what this is. And the idea about this whole domain stuff is that when you do that, you do wind up with newer separate domains. Okay? So functions are, excuse me, you can have inverse functions if you flip your x's and y's. This is something that works out super fast, and it's really all you're doing, and we're going to do something out of slope-intercept form first, it's the easiest way to do it, is in order to find an inverse of a function, all you do is flip-flop x and y and resolve for y. Exactly. So what you're looking at here, if I'm taking this example here, to find the inverse of this, I'm going to switch x and y and resolve. So if I switch x and y, I get x equals 2y minus 4. And then in order to solve for y, what do? Add 4 and divide by 2. So y would equal x plus 4 all over 2. And that's the inverse of 2x minus 4. Excuse me. What do you mean? Oh, I see what you're saying. I would stay away from that because sometimes it's not as clean. Because you have to start thinking about exponents and stuff like that. Okay. Now, what happens with these? Well, let's do another one real quick. I don't know why there's an 8. Try another one real quick, and then I'll show you where this is getting. And as you get into these things, it's not going to be horribly scary, especially when you start working with the linear stuff. When you flip-flop x and y to start, just got to watch when you have the negative, make sure you bring the negative along with it. So you'll have x minus 6, negative 2/3 y. How do you undo multiplying by a fraction? Multiply by its. And then if you distribute that out, what do we get? Was it 9, I believe? And that would be the inverse. Bless you. The inverse of functions, what you can do to verify, to see if it actually, bless you, is an inverse. If you're saying, well, let's see here. Let me rewrite this. Let's move this up. If the way that they talk about this in terms of f of x, g of x, things like that, this function notation that we've been kind of slowly working on, is that if you take a composite, remember that's what we were looking at last week, where you take f of g of x, or you basically surround it with the other one. If you take your two, with the original and your inverse, and you substitute into each equation with them, you should always just get x. If that's the case, then you know that they are, in fact, inverses. So if I go back to the very first one we did, because that was the easiest, that was the first equation we did was what? Y equals 2x plus 4, I think? Minus 4? So the first one we did was y equals 2x minus 4, and then we said the inverse of that was y equals x plus 2, x plus 4 over 2. So if I call this one f of x, and I call this one g of x, just for hoops and giggles. Say it. Easy. So if I just go ahead, because we already know that that's the inverse, we already solved it out. Watch what happens when you substitute in for each other. Now, if I do f of g of x, that means the first thing I do is I write down the g of x equation, then I surround it with the f. Very similar to what we did on Friday. So let's see here. G of x equation is x plus 4 over 2. Now that's playing the role of the x value in the f equation. So I take this times 2, and I subtract 4. Well, order of operations, let me symbolize this. Order of operations, well, what's 2 into that? What happens with 2's? They cancel. So then I get this up sum. X plus 4 minus 4, which is equal to x. Okay. And I do the same thing with the g of f of x. So if I start by writing down the f equation, x minus 4, and that's now playing the role of the x value in g, plus 4 divided by 2. Fractional stuff, when you have order of operations, take care of the stuff in the numerator. What's 4 minus 4? 0. So these two drop. And then 2x over 2 is x. And lo and behold, you get x. Sorry. So it's a lot of substitutions here. A lot of substitutions. The way that we do that, though, is that we read this as an inverse. You guys have an inverse button on your calculator. X to the negative 1. That's inverse. 1 over x. That's the idea. It's what's being called that. So to verify that these guys are in fact inverses, this just stands for that f to the negative 1 of x. That just stands for the inverse of x. So they're telling you that here's your f equation, and here's the inverse of it. If in fact they are inverses, when you substitute in one for the other, you should always get x. So just like we did a second ago, oh, this is the same example, isn't it? Except they wrote it as x plus, I had it as x 1/2 x plus 2, where I had it as x plus 4 over 2. Oh well. Let's pick a different equation then. Let's do this one. Welcome. Does it change when you have powers? No. It doesn't change at all when you have powers. So now this one says verify that f and g are inverses. So in order to verify that they're inverses, you just basically are substituting into each equation, simplifying it. You should get x, especially since they're saying verify that they are inverses. Okay. So if I start with the f of g of x, that means write down the g equation. x to the 1/3 over 2. Now that's playing the role of the value of x in the f equation. So what's x to the 3rd cubed? X. What's 2 cubed? 8. So it works going one way. Then I try going the other. Now this next one is where a lot of you guys make some mistakes. Oops. Write out the f. Surround it with the g. Now this value here is playing the role of the x in the g equation, which means in this case, it's the whole thing to the 3rd power. Whereas some of the other things, like on that worksheet from last Thursday, some of those was just the thing on x to the 3rd. It didn't have it in front of anything else in front. There was no parentheses around it. So you have to make sure you be careful with parentheses. And what's the cube root of 8? What's the cube root of x cubed? X. So this one simplifies out to be 2x. It's not very bad. Inverse of power functions. Do you think anything's going to change? No. Now, one thing I want to show you is, why do you think that they are saying that x has to be greater than or equal to 0? No. Sorry about that. What's happening is that way when you have your, if you think about the graph of this, if I'm looking at just the graph of x squared, the graph of x squared is the parabola, like that, isn't it? Now, since it's only looking at positive values, it means I don't care about anything over here. Okay. Bless you. So you're just looking at these going up like that. So if I flip-flop x and y here, so if this is y equals x squared, when I change that to check for the inverse, that means x equals y squared. So how do you solve for y? You square root it, exactly. So the square root of x, I don't have to worry about plus minus here because it said x is always going to be positive. So that just tells you that the square root of x and x squared are inverses. And if you look at the graph of x squared, it looks like that. Watch what happens. Let me get my calculator out. Nope, I don't have it. Don't care about that. So if I put in my two equations, what I have, x squared. Helps if I actually have an x though. And then the other one was the square root of x. What I'm going to do here, since they asked us for all values of x that are positive, so I'm going to change my window to start at 0. Okay? It's going to go 0 to 10. When I graph that, nope, I'm going to change my other one. There's x squared, or x. Now, watch this. We know that these two guys are inverses of each other, right? Now, if you substitute in one for the other, what do you always get? X. That's the idea. They are symmetrical about the line y equals x. Inverse functions. The inverse functions are going to be symmetrical about that line y equals x. Because if you substitute in for each other, you're always going to get y equals x, or f of x equals x. However you want to write it. So for every one of these, you can get something that looks pretty cool. So all these points that are lie upon, let's back here. Oop, that didn't work. There. So each one of these points are going to be equidistant, perpendicular. Oh, how do I draw that? What is it when you draw through? Whatever. They're all the same distance. Yeah, there's some geometry thing that I forgot. That's right. Where do you think they intersect? Take a guess. 1. At 1, all three of those lines would intersect, wouldn't they? Because if x equals 1, you look at your three equations, just ideal, if you look at your three equations, if x is 1, y is 1. If x is 1, well, what's 1 squared? 1. What's the square root of 1? So you can get into that. All right. Let's try another one. Excuse me. Consider the function. So we're considering now. So we're, using more vocabulary. Determine whether or not the inverse of f is a function. All right. So how do you tell if something's going to be a function? Well, if a function, if you remember when we did this, we talked about this last week, when you graphed something, we took what was called that vertical line test. Remember that? If you could take a vertical line through a graph and it touches one spot all the way around, we knew that it was a function. Now, excuse me, if I look at an equation and I want to know if it itself is a function, I check the vertical. If I look at the equation, I want to see if that equation's inverse is a function, what do you think I would use? Horizontal. So if I have an x squared problem, which you guys know that's an x squared, right? Up like a cup. Would the x squared's inverse be a function? It wouldn't be unless it had a domain restriction. Okay? Now in this case, I just drew up a quick example. There was no implied domain restriction. But if you go back to the other one where we had x squared where it was greater than or equal to 0, if it was that case, wouldn't that would pass the vertical line test because it had that restriction to it. Okay? So it's just those little subtle things you have to be careful with. So if I'm looking at this one, or 1/2 x cubed minus 2, I'm going to throw out my calculator real quick to see whether or not what that graph looks like. Was it 1/2 x cubed plus 2 minus 2? Thank you. So if I look at that graph real quick, come back to my window. Go back to a 10 by 10. Well, that one passes the horizontal line test. Well, we're checking to see if its inverse would be a function. Yeah, it will. This one does. It looks like it doesn't flatten out when you look at that. It's curving through and changing direction. So this one would pass that horizontal line test, which means that the inverse of 1/2 x to the third minus 2 that inverse would also be a function. So if we look at what that would be, it's out of the way. So I have y equals 1/2 x cubed minus 2. So if I flip-flop them, I get x equals 1/2 y cubed minus 2. To resolve for y, add 2, multiply by 2. And then how do you undo cubing? You cube. Will this inverse be a function? You're right, it's doing down up. Where does it change direction at? 0. Change direction at 0. So it's gonna look like it's gonna be something like this. So would that have a function for an inverse? Yeah. So to get the inverse of it, yeah, this is pretty nice stuff. Oop, I went this way, sorry. Something, maybe. Oh. I do a lot of that too. Well, maybe. Now, in this one here then, now, what would you do to rationalize that denominator? How many more? Is it easier to do that with a fraction or an nth root? Fraction. So if I rewrite that denominator real quick as a 10 to the third, how many more thirds does it need? It needs 2 more thirds. Okay. Which gives me 10 in the denominator. This is, if I rewrite that as an nth root, what would that be? So 10 squared cubed, if you will. What's 10 squared? 100. So do these two then have the same nth root? Which means I can combine them. So right now I have the cube root of cube root of x times the cube root of 100 as you put that together. Since these guys have the same nth root, you can put them underneath one radical. All right. The one trick with nth root stuff when you're dealing with numbers, you guys were right by saying that's the cube root of 10 squared. But when you simplify it, square it or do whatever the numerator is first before you put it underneath the nth root. Just a little bit cleaner. Oh, excuse me. Find me an inverse. Okay. inverse of that function. Let's go back. All right. So let's see, we have X. Because I went. Did you get it? Yeah. So what I did is I added this over. I subtracted this, coming back. Divide by -2. You can say thing, right? So if I do it this way, I have 2y squared is 2 minus x. Now, if you had it your way, you had x minus 2 is negative 2y squared. They're still dividing out by the -2, right? So if you divide by -2, you get negative x plus 2 over 2, which is x minus 2. I'm sorry, 2 minus x, excuse me. All right, it's the same thing. I just messed with time. Whenever I have negative variables, I always make them positive. I always move them. It's just my habit. Okay. Then I would, like I said, I had it divide by 2. You get the square root. Now, the reason why they put this on here that the values of x have to be smaller than or equal to 0 is because if I substitute a negative value in for x, it becomes positive. It becomes paradoxes. Just take the coupon out for your copy. Huh? Took a picture. Oh, okay. It should have been. So there's a coupon in there for a free coffee. Do those. I know, right? Get out. What do you want? Shut up. I'm allowed to get. You could have gone to the video and scrolled to the very end. Oh, yeah. Sorry, I'm trying to make your life easy by having stuff taken care of. It's the one time I didn't put something on there. Or you could have, written it down. Here, I'm going to do this right now. I'm going to copy it, and I'm going to go ahead and just make sure that your life is easy. See? But then I also going to do this for you right now before you forget, because I'd hate for you to email me in 20 minutes. Oh, there was? Oh, nice. So I'm uploading everything right now. I'm even going to make sure that you can look at it, because I'd hate for you not to be able to do your homework and have an excuse. And I'm even going to hit save.